do it. It's to one of them, yes. There are multiple Kristens involved with this. Okay, check. 1, 2, 3, there we go. All right. Well, my name is Jonathan Feagle. Hi. And this is my colleague here, Crystal Alexander. I've worked with Crystal over a number of years as Montessori educators, and I can honestly say that she is the teacher I've always wanted to be. So we're very lucky to have her here, and she's going to demonstrate some lessons for us. So I'm going to try to keep it really short, about 20 minutes, and then I'm going to turn it over to her. We can watch some demonstrations. I'm going to talk a little bit about what research says about best practices for the use of concrete instructional materials, and why we think the Montessori model is a good exemplar for the use of those, or implementing those best practices as described in research. But the first thing I want to do is kind of step back a little bit, and I find it kind of interesting to try and take an historical perspective to this topic. And so just kind of bear with me for a second. I'm curious what some of us might think are what would be examples of the first concrete instructional material in history. Right? Does anybody have any ideas about what that might be? Abacus, we want, yeah. So sometimes I get fingers, right? Sometimes the fingers. Abacus is definitely one of them. And even though, see, you guessed right. That's perfect. Right. So even though they weren't designed primarily as instructional materials, looking at them as, in this case, as the abacus, as a mathematical manipulative, is very helpful. But they were instructional also in the sense that someone had to learn them to use them. Right? So people in the society had to be taught how to use them for whatever practical ends that they were designed for. The abacus here is representational in a couple different ways. One, it represents the amount that someone is using it to keep track of. And it also represents the historical process that led up to the creation of an abacus. So initially people would draw their finger through sand and make grooves in the sand and move rocks and pebbles and shells through the grooves. Then they would have a board, and they would chisel out, carve out grooves in the board and use those grooves to move up pebbles and rocks and stuff up and down. And then finally someone had the really innovative idea of just putting it all together. They can carry it around, and you're not going to lose the rocks. Everything stays together. This is Inca quipu, and it's a series of strings, and there are knots on here. And the place that the knots have on the strings determines the value of that knot. So it's a good exercise for place value. And it was used by the Inca Empire around the 15th century for record-keeping purposes, as an aid to memory, for commerce probably. Here you can see a diagram that explains how you use it. And I've used this with lower elementary students. It can be fairly effective if used at the right times. And so we can see here that we have the number 113. There's one knot in the hundreds place, one knot in the tens place, and you have 3 lashes before it's knotted over there in the ones place. And this is also from the Inca Empire. This is a upana. And while the quipu was used for record-keeping purposes, the upana was actually used for calculations. What I find interesting about these historical examples is their practical nature and the way that they were used. So while they weren't used as instructional materials primarily, they were actually the curriculum sort of the society, in the sense that these were the things that people had to learn to use in order to be contributing members at certain levels in their society. So in terms of education, this is kind of what was used. They were used primarily as aid to memory for commerce, sometimes for cultural transmission, weaving baskets. So if you think about reeds to weave baskets, or wool to weave rugs, or clay and earth to make pottery. We don't think of those things as concrete instructional materials, but in those contexts, they were used for activities that represented stories and had significant cultural significance for those societies and was used sort of as a way to sort of maintain memory of the culture over multiple generations. So with that historical context in mind, I'm going to shift really quickly to what we would think of as modern concrete instructional materials, and the differences there, and looking at the way we use them and how they're different, and the different questions that come up because of that is very helpful. So for modern concrete instructional materials, right, they're designed primarily as instructional materials, and so that makes them a different kind of thing. They provide users with information for further learning, right, as opposed to some just further practical purpose. And they don't bear the same burden, or at least not in the same way, as the historical objects did in terms of being an aid to memory. So that's certainly part of why we use concrete instructional materials, is to kind of aid the memory. But there's also a lot of other aspects that come into it. So if creating concrete instructional materials using hands-on manipulatives in educational settings didn't really come about until till the 18th century. And Feagle was one of the first people to do it. Of course, we all know who Feagle is, right? He was the grandfather of, or the inventor, or however you want to call it, for kindergarten. And he developed a lot of materials for kindergarten, and they were called GIFs, or Gaben in German, the Feagle Gaben. And this is GIF number 5, and there was a sequence of GIFs, and there were all blocks and materials that were designed for particular instructional purposes. Seguin was a French doctor, and he was about 40 when Feagle passed. And Seguin worked with children who had cognitive impairments and had a lot of success using hands-on manipulatives that he would design and bring back to the students and see how they do, and then redesign them based on how the students interact with it. And this is the Seguin board that was adopted really whole cloth into the Montessori model. Some of the materials in the Montessori model were developed by Maria Montessori herself, obviously, but some were also designed and created by people before her and after her time as well. And so by the time Montessori, she was 10 when Seguin passed, and I'm noticing those markers just to kind of give you a context of time. She was about 10 when Seguin passed, so by the time she was creating her model and creating her materials, the idea of using hands-on materials like this, and the fact that you could actually design things, as opposed to just using materials that were already around, that you could actually design things to use for instructional purposes, had been around for about 100 years. And so you can see the influence of Feagle here, and this is same logic as an abacus. Of course, this is a rec and rec, and this is was designed by someone who was a contemporary with Montessori, and gives you an idea of the fact that there were other people inventing these things. Of course, as technology advances, our ideas, concepts of what we consider to be concrete instructional materials expands a little bit. And even with software, would we think of software as a concrete instructional material? But so this is a virtual representation of the Montessori 100 board, and here you can count to 100 or count by twos. And this is sort of the same activity, but it's mediated by a screen and a mouse, as opposed to a wooden board and tiles. So there is a real sense in which this is a concrete instructional material. So we can think of software as a concrete instructional material. The use of modern manipulatives, modern concrete instructional materials in an educational setting raises two important sets of questions. And one is around this concrete abstract distinction, and the other is about the question of transference. So with concrete and abstract distinction, right, where we think of the materials as being concrete, but they're leading us to something that's abstract that we're going to learn. And then, of course, the way that we define concrete abstract sort of sets up the way that we approach the problem of transference. Right? How do we move from one to the other? Let me talk about the concrete abstract distinction sort of really quick. I'm using the word, we tend to use the word manipulative and concrete interchangeably or not quite synonymously. But when we think of the word manipulative, or when we use the word manipulative, we're focusing on the fact that the object is something that the student can manipulate to inform their learning. So, for example, if they look at it face on, it looks like a two-dimensional square. If they turn it, there'll be some volume and depth to the object. If they set it on the face, it just sets there. But if they put it onto the corner where the three lines or creases come together, it'll fall back down onto a face. So we can begin to make causal inferences about the way these objects behave based on our own interaction with them, and that informs our learning with these objects. We'll use, that's sort of in contrast to a typical traditional textbook, which is, you read, has information in it, but you don't really manipulate it, right? At least you're not supposed to. We use the word concrete when we want to focus on the fact that the object is in three-dimensional space, right? It has shared visual space. We can all point to it. It has physicality to it. And that's sort of in contrast to ideas in our mind that we sort of, manipulate in our mind, and we tend to not think of those things as being concrete. But setting up the distinction like that, it has a couple of different problems. One, we tend to sort of think of concrete as being one kind of knowledge, and abstract knowledge as being sort of different in kind, and we don't really see it as on a spectrum always. And so the question of, well, how do you go from one to the other, right? It becomes a very difficult question to manage if we've set it up to where they're very different things. Also, the fact that the concrete objects aren't actually as intuitive as we sort of assume that they are. So we think that the concrete abstract distinction is important, and it's helpful to, we want to move from the concrete to the abstract because we sort of grant a privileged status to concrete materials because they're more intuitive, more transparent, and they'll help the students sort of move to the abstract and to understand how to use the symbols, to gain fluency in the symbolic notation that tracks those abstract reference. The concrete instructional materials are designed to sort of teach us. But so remember the Upana, and the first time we saw this earlier, right? You probably experienced a certain amount of wonder, like that's really cool, but also kind of confusion because I have no idea what that is. Right? It was used for to make calculations, but if for us looking from the outside, this looks just as abstract to me as a set of symbols, and so that kind of puts us in the position of what a child would sort of see when we present them with concrete instructional materials, keeping in mind that just because it's concrete doesn't mean that it's not abstract, right, in some ways. So Doug Clements and colleagues have, over a number of years and a number of papers, described or put forth a distinction between two different kinds of concrete knowledge. And the first kind is concrete in the sense that I was talking about it just a minute ago. It's there in shared visual space. It has 3D physicality. And so when we have sensory concrete knowledge, it's because we can manipulate the concrete instructional materials correctly to get the right answer, right? Even though maybe we can't do it without those materials. Integrated concrete knowledge uses the meaning of concrete in its most literal sense. Concrete means actually to grow together, right? It's from the Greek concrescere. And when we think about how we make concrete, it has different things come together to make it. You have cement, and you put water in it, and you have some substrate, and you mix it up, and and you shape it, and it becomes this sort of really hard, solid substance that has qualities in it that we can't really find in any one of the elements that goes into it. And so what gives concrete, right, its strength is the bonds between the different elements that are in it. And so integrated concrete knowledge is knowledge that a student has that combines their abstract understanding, their fluency with symbolic notation and language, written language, as well as the concrete experiences that they have using not only concrete instructional materials, but also just all the concrete experience that we get throughout life, right? So, for example, if I'm going to add 42 and 23 in my head, I can treat those objects, I can treat those numbers in my head like physical objects by popping off the 2 and the 3s from the units place, and adding them together and then and putting everything together for the answer. One really good example, which is slightly personally embarrassing, but it makes it actually demonstrates the point very clearly, is, growing up and going to school, I did math, and math was always, fairly easy to me. I didn't do a lot of it, and I wasn't like great at it, but it never presented a problem. I never really was forced to think about it too much. And so I could do, 3 squared is 9, and I understood how to do squares and square roots. And but when I was going through my Montessori training, and we were taught the lessons on how to teach kids squares, and eventually how to do square roots, they put the square of 3 down, and I was like, oh, that's why it's called 3 squared, because it actually makes a square, right? And that just had never occurred to me. And so that, combining that, being able to sort of see it geometrically and understand it sort of from a physical point of view, combined with how I understood it symbolically, made my knowledge much stronger, right? It was integrated concrete knowledge as opposed to just some abstract understanding. That became really powerful when I realized that when you want to find the square root of a number, especially large numbers, it's basically a function of taking that number and making it into a square, and then taking the value of the bottom row of that square. And how do you do that in such a way that it accounts for place value? It's a very powerful way to think about it. So the big question, right, how do you go from over here to over here? How do we go from the use of these concrete instructional materials to fluency with this symbolic notation? This is the Pythagorean Theorem. But if you're not familiar with this, or you're not familiar with this is one of the Pythagoras plates in the Montessori model that's used to teach elementary students the Pythagorean Theorem. But if this looks, alien in much the way the Upana did, that's good, right? It just reinforces the fact that the concrete instructional materials can be just as abstract, right, as the formula over here. So how do we use these materials to be successful and set the students up for success? Right? Can we just take that material and set it in front of the students and hope for the best? It turns out you can't. There's actually some things that the students need in order to be successful with concrete instructional materials. And some of the things that can go wrong, the reason why success is not always guaranteed, is sometimes there are extraneous perceptual details that get in the way, that serve as a barrier to learning. Sometimes the materials distract the students from thinking about the underlying content that the teachers want the students to think about. And what a lot of research has sort of found out is that teachers don't always address that transference, the relationship between the concrete knowledge and the abstract symbols that they're connected with. And so what are some theories for why this happens, right? Well, one is teacher perceptions. And it turns out that not all teachers, a lot of teachers use concrete instructional materials in their classrooms, but they don't actually believe in the efficacy of the concrete instructional materials. And so there was one case study on middle school teachers, and they quoted one of the teachers that they had interviewed as sort of summing up really the essence of their findings. And she said, well, I don't mind using the materials. I don't mind that they're having fun with them, because eventually we're going to get to the real math, right? And so essentially it was sort of like using them to kind of get the attention of the students and kind of do a bait and switch, right? Once you have their attention, then you pull out the real math, right, the symbols. Another one is dual representation. So when we use concrete materials, students have to represent that material to themselves as the object that it actually is, in addition to being representational of underlying mathematical content, or just underlying instructional content that the teachers are trying to teach them. And that puts an extra strain on their mental economy. Another theory is the structure of the environment. By structure of the environment here, they primarily are referring to teachers' classroom management styles and strategies, instructional styles and strategies. And for example, if students are allowed to interact with the concrete instructional material before ever having a lesson on it, they can develop a certain meaning with those materials that isn't necessarily, excuse me, that isn't necessarily analogous to the underlying content that the teachers want to use that material to teach them. And that throws up another barrier of learning. And then, as I mentioned previously, addressing the link between concrete and abstract representations isn't always done very effectively. All right, so what does this mean for us, right? Because of those theories that I just sort of went through about why concrete instructional materials aren't always successful, well, it turns out that we have to be very careful when we use objects that are familiar to students in non-learning contexts. So if we're using pizza to teach fractions is something that we should sort of maybe think about that. Maybe it's good as a refresher for older students, but when you're first introducing the concept of fractions, it might be better to use things that are not familiar in a outside of a learning context. You minimize the use of objects that are rich in perceptual detail because there's a lot of competing detail. It distracts the students away from the underlying content. There are exceptions to this, especially with older students. Sometimes competing detail is a good learning opportunity for problem solving and weeding out what's important from what's not. So there are often reasons for quote unquote extraneous perceptual details. And third, to address transference. So how do we go from here right to here? Well, assuming that we have a classroom with materials that are designed and are not familiar to students in outside of learning contexts, and we have teachers that are trained in using the materials and really believe and understand how to use the materials, and they have the right structure, et cetera, then what do we do, right? What do we do with these materials? Well, one of the more robust theories of addressing the question of transference is this theory of concreteness fading. Thank you. It's based on the work of Jerome Bruner, who had an instructional theory that concepts and procedures should be presented through three different phases, through an inactive phase, an iconic phase, and a symbolic phase. An inactive phase is, for example, if you're learning a play, and so you're acting out the play on stage, that's inactive. Then later you might draw a scene from that play, and that's iconic. And then later you might write about the scene or write about the play using symbolic notation, i.e., in written language, and that would be symbolic. Concreteness fading posits the use of multiple concrete examples. So you start with something really concrete, and then you use different examples that takes away some of the physical cues, right? The objects become more abstract as you move along this continuum. They're ordered in a sequence for that reason. And you focus on mapping each of those concrete examples to the abstract reference that you're trying to draw the students' attentions to, as opposed to having students map the similarities between the objects, because that sometimes results in students making connections that aren't analogous or don't have any connection with the underlying content. To address to get to Montessori, Montessori called her theory she called it experimental psychology, and what really drew her to develop the model in the way that she did was certain experiences that she had with young children where they would seem really just engrossed in their work, and they would repeat exercises over and over again, and when they finished and they came out of that activity, they appeared to be more expansive, more peaceful, more intelligent beings. And she saw that as almost kind of she approached education because of that sort of more as almost as a psychological endeavor, really, not as one of transmitting content, but a psychological endeavor, even a spiritual endeavor, right, if you will, because it was something that sort of changed who you are. Right? So from that point on, she thought, well, there must be some science to set up. There must be some way to sort of scientifically determine what the best environment would be to maximize the number of these kinds of experiences that students can have. And and she was a hardcore scientist. She was a female doctor, first female doctor in Italy. She would, over a course of a number of years, she took on a set of experiments that she actually attributes the idea of it to Seguin and Itard, where she would present materials to students, and based on how they interacted with those students, she'd go back and change the size of them, the color of them, and make various changes to it until she had materials that students would interact with and would spend a lot of time with it. And it would seem to sort of correspond, that material would sort of seem to correspond to some sort of internal developmental need in the child. And once there was that correspondence between the materials of what she called the external stimuli and the internal development of the child to create that kind of experience, that kind of very positive learning experience for the child, those materials or external stimuli were considered to be factors of development. And so, there's obviously a lot more to the Montessori theory, but focusing just on those materials and thinking about those materials as not just something that sort of transmits content, but something that can lead students along a path from concrete to abstract understanding, but not just abstract understanding, but integrated sensory knowledge, and also not just of leading them along a path where they understand content, but also being providing experiences for development of their overall sort of psychology, right? So on that note, I'm going to go ahead and stop. I'm going to turn it over to Crystal, and she's going to demonstrate some lessons that exhibit this path from concrete to abstract.
First of all, I'm going to go ahead and go through all of the transference and the concrete to abstract, like he said, but a couple things about Montessori. We do all of our lessons on the rug, so I will have a small group of children that, during formative assessment, I have decided are ready for these lessons. I've taught preschool, TKK, and now I do elementary 1st through 3rd. I did have like 4-year-olds and 5-year-olds that were able to do a lot of this work. I'm just going to do simple static addition with you guys today. So first of all, I would introduce the students to the golden bead materials. In Montessori, we always say unit. I know it's kind of an antiquated term now, so I will say unit and 1. So this is a unit, also known as a 1. If we have 10 of these units, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we have a 10 bar. If we have 10 bars, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, we have 100 squared. If we have 10 hundred squares, we have 1,000 cubes. 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000, or you can just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1,000 cubes. And then I would introduce, probably not in the same lesson, the symbols. So we all know this is 1, our unit. This is the quantity. This is the symbol of 1. This is the quantity of 10. This is the symbol for 10. This is the quantity of 100. This is the symbol for 100. This is the quantity of 1,000. This is the symbol for 1,000. And then typically the Montessori teacher would do a 3-period lesson. So the first part is introducing, The second part is asking the children to can you show me the symbol for 1,000? Can you show me the quantity of 100? And they will point to it as you're doing it. And then the third part of the 3-period lesson is show me, or what is this? And they'll name 1,000 cube. What is this? The quantity, or the symbol for 10. What is this? The quantity of 10, or a 10 bar. So that we pretty much do that across the board in Montessori education. And then when we're putting things back, we'll ask the students, can you put the 1,000 cube back in the tray? Can you put the 100 squared back in the tray? Put the 10 bar back in the tray? The unit back in the tray? And then the same with the symbols. So for very young students, and you've done a lot of composing numbers and gathering numbers before you do adding, so they're very familiar with the golden bead materials at this point. So you can give them a problem, a couple of add-ins, 1,111 is the first add-in. And then we use the small wooden numerals, plus 2,222 is the second add-in. So let's go ahead and build our first add-in. We have 1 unit. One 10. 100, 1,000, plus 2 units, or 2 ones, 2 10 bars, or 20, 200 squares, 100, 200, and 2,000 cubes, 1,000, together. So we have 3 ones are units. And then we'll use the bigger numbers at the bottom to show that 2 smaller numbers make 1 bigger number. 3 10 bars are 30. 300s. And 1,000, 2,000, 3,000. Oops. So we've learned that 1,111 plus 2,222 is 3,333, and we can double check with our quantity if it's out there. And then I would have them help me put these back to you to reinforce place value. So this is the golden bead material. And then if you notice, this is color coded. Okay, so then the next one is the stamp game, the next material. So I would get the presentation tray out again. So we all know that this is a 1 or a unit. This little stamp is a 1 or a unit. And depending on the age, why do you think this is called a stamp? And they usually, oh, like a postage stamp, although that might not work too much longer. Right?
I was thinking rubber stamp.
Right.
Yeah, that's what I was thinking.
See, it's already being known.
Phasing out, yeah.
And then we know that this is the quantity of 10 on our golden beads, our pretty shiny golden beads. This is also 10. So this is the quantity of 10, and this is the quantity of 10. And we have our lovely hundreds squared with 100 little ones on there. And this is also the quantity of 100. 1,000 cubed with 1,000 little golden beads in there. And then this is also the quantity of 1,000. And then we could do a 3-period lesson also. We're going to go ahead and do some adding with them. So you could also use these materials for this, or you can write it on a whiteboard, or you can have it written down for them. For young kids, I wouldn't have them necessarily record it because they're still learning how to write their numbers, how to form their numbers. So a lot of it is just doing it and not recording it. So we're going to go ahead and do the same problem. So 1 unit, or 1, 110, 100, 1,000 plus 2,222. Start by putting our units out. 1, 2, 2 tens are 10, 20, 200, 100, 200, and 2,000, 1,000, 2,000. Add them together. So we have 3 ones, 3 tens are 30, 3 hundreds are 300, and 3 thousands. So our sum is 3,333. That's the stamp game. And golden beads and stamp game can be used for all of the operations: multiplication, division, subtraction. And then I would get out the tray again to introduce the next material. And some people will also get the stamp game out too. Okay, so our next material is the bead frame. So this was our unit. This right here is also a unit or a 1. This was our 10 bar. This is also the quantity of 10. And then this is the quantity of 1,000. This is also the quantity, 100. This is also the quantity of 100. This is the quantity of 1,000. And this is also the quantity of 1,000. I'm not sure how much time we have. Okay. Do I have time to my adding on this one?
Yeah.
Okay. Okay. Okay, so then this is the bead frame. So we're going to go ahead and just, for the sake of time, do the same problem. So 1 unit, 110, 100, and 1,000. So our second add-in is 2 units, 2 tens, 2 hundreds, and 2,000. And then we would go ahead, okay, 3 units, 3 tens, 3 hundreds, and 3 thousands. And this one you can do all of the operations except for division. And there's also a bead frame that goes to the 10,000. Right, or 100,000, 100,000. Okay, so the last one, right before abstraction, is the dot board. So this one I'm going to go ahead, using the same colors that we've been using all along, write out the math problem. So we're going to go ahead and add 2,544 plus 2,163. So we're going to start with our first add-in. And a lot of time, as you're going through, you're having the kids tell you what the numbers are. It's not always the teacher. So 4 units. So 1, 2, 3, 4. 4 tens. 10, 20, 30, 40. 500s. 100, 200, 300, 400, 500. And 2,000. Oops, I need to do black. 2,000. Okay, then we're going to do our second add-in. 3 ones. 3. 6 tens are 60. 1, 2, 3, 4, 5. Oops, I shouldn't have done that. 6. Guess what? We're going to learn some dynamic.
I wondered about that.
So then we're going to go ahead and cross these out and exchange it for 100. And then we have to put our 100 in. And then our 2,000s. Okay, so we have 1, 2, 3, 4, 5, 6, 7 tens. Or 7 ones, 0 tens. 7 hundreds. And 4 thousands. So now we're going to go ahead and put it in standard form. 7, 0, 7, 4. Okay, can someone read that to me? 4,707. And then you can have them write it up here. So we know that 2,544 plus 2,163 is 4,707. That's a weird looking 7. You can put your comma in there if you want to. Got word. And then hopefully after that, they're ready for abstraction. Oh, are there more than one of the materials in the classroom? Yes, there are, but they're not enough for everyone. So the classroom is designed to be an extension of your home. So we don't have desks. The children are doing their work on rugs. We do have tables, so they do some of their work on tables. Their classroom set up like there's a math area, language area, and the materials are set on shelves. So after I do the presentation, the lesson on it, and he was talking about how, it's not always productive for a child to just see a material and play with it how they want without a lesson. So a lot of, especially in preschool, teachers will have like the things that they haven't presented wrapped are not on the shelf because everything in a Montessori classroom should be for the child. So if you don't want them to use it, then don't put it out or have it wrapped, so it's distinguished. And then it's a big production when you're doing the lesson. You get to unwrap it very, gracefully, and the kids are excited. But once it's out on the shelf and it's their math time, they would like to do a math job, then they would get it out, lay their rug out first, get the materials out, and then use it, put it back on the shelf where they got it from, roll their rug up and put it away. And they get really good at it. It's amazing. I mean, of course, there are some times when they don't. And then we talk about how the rug is to distinguish that this is their work area and their materials, and nobody else is invited to touch it unless you invite them to. And, we go through a lot of lessons on how to walk around the rugs and how to carry materials. Because you can't carry the stamp game all crazy because they'll fall out. So they learn how to carry it very respectfully and gracefully through the classroom. If I do a lesson and everyone wants to use it, they grace and courtesy, so they just wait until their turn. And the material is put back on the shelf before someone else can take it off. So they're not just switching rugs. They're putting it back on the shelf where they got it. And then that reinforces, cleaning up after yourself, but also where materials are on the shelf. So hopefully we're not running into math materials over in language and no one can find it. And it's all crazy that way. Good question. Anything else? No? If you guys get a chance to go into a Montessori classroom, it's very different and it's amazing. It's beautiful. And everything's wood. There's not, we don't like plastic. So we have a lot of baskets and wood and children's artwork displayed in frames, plants, animals, all kinds of animals. And it's their classroom, so my kids take care of the animals and the plants. Anything else? Nothing? Any questions online? No?
Well, thank you.
Thank you.